We're going to now start looking at formal tests of convergence and divergence for series. So up to now, we've kind of done informal testing of divergence and convergence of series. This is a formal test now, and this formal test involves testing the nth term of a sequence. So we're going to test the nth term of sequences. In fact, we're going to test the nth term of two sequences, and then we're going to make some conclusions about the series. So the test is this, the limit comparison test. This is what it's called. And it says that if the series of a to the n, so sum of the a to the n terms, and the sum of the b to the n terms are non-negative terms, that when we compare the ratio of the nth term of a to the nth term of b, we want it to equal a limit. And that if that limit is bigger than 0, then they both either converge or you both diverge. So essentially what it's saying is this. If when we compare the an term to the bn term and we get a limit, the behavior of an and bn are relatively the same. Okay, they behave in the same way. If they behave in the same way, if one converges, the other converges. If the one diverges, the other must also diverge because of the similarity of how they behave. And we come to this conclusion of similarity because if it comes to a limit, we know that those two terms as a ratio must be similar to each other. Okay, so what we need to do is, how we use this test is, if one of these is a known series, okay, so for example, if B is a known series, converging or diverging, we could try to set up this test so that we can try to see if we can get the known series to match the unknown series, in this case A, and we're looking for this limit equaling some number. And once we get the limit equaling that number, we can say that they behave the same. So if B was a converging series, A converges. If B is a diverging series, A diverges. Okay, so let's see what this looks like. So the first example here, we're looking at this series that we want to determine whether it converges or diverges. Now, in this case, I've told you that we should compare it with the divergent series 1 over n. But there's a reason why 1 over n was selected here. And it's because of this. When you look at this series, the terms of the sequence is going to be 2n plus 1. So the degree of the numerator is 1. And then if we look at the degree of the denominator, n plus 1 squared, the highest power is n squared. So when we look at the power of this function, or the strength of this function, it's going to be n divided by n squared, or essentially, for large values of n, it's going to behave like 1 over n. So that's why we're choosing this 1 over n as our comparison. For one thing, we probably should kind of start leaning towards the fact that this might be a diverging series. And so we want to choose a diverging series that is similar to the one that we are trying to make conclusions on, which is the red one. So we set up the limit comparison test like this. So now this becomes the formal way we show this test. So the limit comparison test, we take the limit as n approaches infinity, and we're going to take the ratio of an unknown series term or unknown sequence term to the known sequence term. So the unknown one that we're testing is this, 2n plus 1 over n plus 1 squared. And the one that we want to compare to, the known sequence that we want to compare to, is a 1 over n. And we're looking to see if this ratio equals a limit, some number limit bigger than 0. Now, before I apply the limit here, I'm just going to rearrange this so that it's easier to work with. We just want one fraction. So we're going to put the numerator parts on top and the denominator parts on bottom. So the 2n plus 1, that goes on top. n plus 1 squared goes on bottom, and then here we have times n, and then the 1 goes down here. So we're going to then apply the limit. So the limit as n approaches infinity of this expression. So to expand, I'm going to expand this expression out. So I'm going to get 2n squared plus n over n squared plus 2n plus 1. We know that these terms are insignificant. So we can just compare the highest powers, and we can see that the highest powers essentially cancel out. So then the limit then is equal to 2. So when we compare the endpoint behavior of the sequence AN to BN, we know that we get a limit, it's equal to 2. What that means then is that they behave in a similar fashion. Okay, if they behave in a similar fashion, then what the conclusion we're going to make is that they also, if one converges, the other converges, if one diverges, the other diverges. So it looks like this. Our argument then becomes this limit is greater than 0, therefore they behave the same. Okay, if they behave the same, because the series, so the series the series 1 over n, this is divergent, and we know that then because they behave the same, we know that this series must also be divergent. Okay, so we know that this must also be divergent. Okay, so and 1 over n is divergent. It behaves the same as 2n plus 1 over n plus 1 squared. They must both be divergent. So when we're doing this, we're testing the nth term, okay, and we're going to do this in a ratio. We're going to apply a limit to infinity, and we're looking for this result. We're looking for the result equaling some number, a non-zero number. If that's the case, then we say that they behave the same. So if one converges, the other converges, one diverges, the other diverges. So we'll try another one here. So this series, we probably should again have a sense of whether this is going to converge or diverge, and once we establish that, we hopefully we have enough experience to kind of think there are some series that we already know that we can compare it to. So this is 1 over 2n minus 1. This is essentially geometric. So when we compare this, we're thinking this is probably going to converge. So I'm going to compare it to converging series 1 over 2n. And I'm choosing 1 over 2n because it is geometric like the one that I'm trying to make conclusions on. Okay, when I'm trying to decide if this converges or diverges. So this is my known series, and it converges. So if I apply this limit comparison test, I want to try to make it behave the same. So it looks like this. My limit, so the limit as n approaches infinity. Now my unknown term, and it doesn't actually matter for the limit comparison test whether your unknown is in the numerator or denominator, as long as you end up with the limit. So for example, this one, if I flipped it around, it would equal 1/2. However, 1/2 is still greater than 0, so we still come up with the same conclusion. So if you want to switch it up, you can put the blue on top and the red on bottom, but I'm just going to keep it the same. I'm going to keep the unknown on top. And I'm going to put the known series on the bottom. Okay, I'm going to rearrange this so that this is a little bit easier to look at, because when I'm doing limits, I don't want complex fractions. I want one numerator, one denominator. So I end up with 2 to the n in the numerator, and I end up with 2 to the n minus 1 in the denominator. And we can see that this is going to be a ratio, the exponential divided by exponential, that's equal to 1. Okay, this is key. So if it's equal to 1, that means it's bigger than 0. It is a whole number, it's a finite number bigger than 0. So what we can say then from this is, therefore, because it equals a limit bigger than 0, they behave the same. Okay, so that's my conclusion that I get from the limit being a non-zero finite limit. Okay, so they behave the same. So if they behave the same, we're going to say that the series 1 over 2n converges, and that also means then that the series we're testing, 1 over 2 to the power n minus 1, also converges. Okay, so now we now have established formally, using this limit comparison test, that 1 over 2 to the power n minus 1 is a converging series. Now again, this is the first formal series that formal test that we're gonna do, and we need to set it up a little bit more formally, and we can come up with these conclusions.